Hello IB, let's now have a look at 22I, which is some of the laws of probability. So the first one we're looking at here is where we have combined events. For example, if we asked in class who likes chocolate and who likes swimming. Are these mutually exclusive? So you need to get used to these terms. Mutually exclusive, does that mean the people who like chocolate are totally different to the people who like swimming? No, we could have some people that like both. And that's evident in when we draw a graph like a Venn diagram like this, where there's an overlap. So some people can like both. So when we have these two events, if we want the union of the two things we're looking at, in this case liking chocolate and liking swimming, then we can get the probability of getting liking chocolate or liking swimming. In other words, P, A or B is the probability of A plus the probability of B minus the probability of A and B. So in other words, it's basically saying that if I want to choose the people, what's the probability of getting someone who likes A? That means all of those people, or whoever's in that category. Then for B, it's going to be all of these people. And what you see is we end up counting the people in here twice. We count them once with the A's, once with the B's. But we don't want to count them twice, so we subtract one lot of the overlap of A and B. So that's that relationship, and that just accounts for the fact that we've done the double counting. So in common language, what does that mean? The probability of either A or B or both, that's what we mean when we take A or B. So it's the whole lot. It's all of this region, A or B. Then it's the probability of A plus the probability of B minus the probability of both A and B. So let's do this example. If we know the probability of X is 0.6 and probability of Y is 0.5, we know what the union is, what's the intersection. In other words, what's the probability of choosing something or someone that has X and Y, just simply using your formula. So your probability of X or Y, going from this formula up the top here, equals the probability of X plus the probability of Y minus the probability of X and Y. Substituting in the values we know, so we know X or Y is 0.9, probability of X is 0.6, probability of Y is 0.5, minus the probability of X and Y. So therefore the probability of X and Y will equal 0.6 plus 0.1 is 1.1. We've added that to that side. Now let's subtract our 0.9 and it comes out as 0.2. So that's a probability of getting that overlap between A and, well, between X and Y. Could we have done this with a tree diagram? Could have we drawn that up? Always think about how you present your work and what fits with it. We can't obviously do this with a tree diagram because in a tree diagram all the branches are mutually exclusive. If you either have X or Y, so to have X and Y isn't possible. So no, you can't do that. So these are mutually exclusive. So in here, let's just put this into a Venn diagram to make sure you're used to that. If we know the probability of all of X, nice round circle, is 0.6, that's a 6 and that's a 0. And we know that all of Y, all around here, is 0.5. But we have this overlap in the middle, and we found out that our overlap is in fact 0.2. So if that's 0.2 in here, then out here must be only 0.4, because we subtract the 0.2 from there. Subtract 0.2 from 0.5, and we end up with 0.3. So in other words, we could just draw our diagram up with x as 0.4 in this region, 0.2 here, and this is 0.3. Remembering this is our universal set. If that's a universal set, then altogether we must have a probability of 1. They add up to 0.9, which means there must have been a 0.1 probability of not being an x or y. Mutually exclusive or disjoint events. So that's when there's no overlap, like we talked about. The last example, there was an overlap. You could like chocolate and you could like swimming. So we could do the same like those who are doing physics in class and those who are doing chemistry, we have an overlap. But there's no overlap in terms of students that do, say, SL and students that do HL. You can't do both courses. You either study SL or you study HL. So they're mutually exclusive. There's no overlap. So that intersection is 0. So the probability of A or B is simply adding up those probabilities. And that's what you're doing in a tree diagram. When you're going vertically, you're adding probabilities because all the branches of a tree are mutually exclusive. So here you're just going to be adding these different probabilities as you go up and down your tree. All right, so let's have a look at this example here. A chocolate is randomly selected from a box and contains 6 chocolates with hard centers and 12 chocolates with soft centers. H is the event of randomly selecting a hard center, S is for soft. Are the events H and S mutually exclusive? What do you think? Hopefully you've said yes, because the center is either a hard center or a soft. You can't have it both ways. What's the probability of H of getting a hard center? It's simply going to be the number of hard centers is 6 out of the total number. 6 plus 12 is 18. So there's a 1 in 3 chance, a third. So that one's easy. What about the probability of getting, let's just do this one. The probability of soft center is obviously going to be the complement of that. Will be 2/3 or 12 out of 18. Number 3, what's the probability of having a chocolate that is hard and soft-centered? Not possible, because they're mutually exclusive. So that relates to this. And what's the probability that you pull out a chocolate that is either a hard center or union, a soft center? Well, definitely, probability of 1. Conditional probability. Conditional probability is an important area, and you'll come across this a lot, and they like to make these the trickier questions. The conditional probability was talked about in the previous video, where we have a given situation. So if we've got 2 events happening, the conditional probability of A given that B has happened. So the giveaway word here is that given. All right, so we're given A and B. That's the word we're always looking for carefully to see if that sort of word or if that word is present. So that's your indicator that you've got a conditional probability. The notation here is with the A and that vertical line. It's on your keyboard above the backslash. So it's a vertical line, it's not a divide sign, and it says A given B. So let's look at this example. You've got a class of 25 students, 14 like pizza, let's go P for pizza, and 16 like iced coffee. 1 student likes neither, so we've got 14 liking pizza, but that's all of pizza. We've got 16 that like all the people that like coffee. One student likes neither, so we've got someone out here. 6 students like both. So if we've got 6 here, then out here we need to change. We're only going to have 8 students because there were 14 altogether. And here we don't have the 16, we've only got the 10 students. So 6 and 10 makes 16. What's the problem? So could we do this on a tree? No, because they're not mutually exclusive. Someone could like pizza and like coffee. So probability that they like pizza is simply going to be the 14 that we've got in our pizza circle there. Total number of people we've got, 25 students. The second one, what's the probability they like pizza given that he or she likes iced coffee? So given that they like iced coffee, so that means given that they're in this circle already, so you're just looking at this circle of the 16 people, what's the chance they like pizza? It'll be that 6 out of the 16. So the probability of liking pizza, straight vertical line, given that, a bit like the domain symbol, given that they like coffee, is going to be 6 out of 16. All right, let's make that look a little bit neater. Okay. So the formula here is the probability of A given B is the probability of getting A and B. So that's our A and B, the P and C, in this case. We've got the probability of liking pizza and liking coffee, given that out of those that like coffee. So we're just looking at the coffee. So you need to know that formula. It's in the formula booklet, and you need to be able to translate it and use the symbols that you're working with. So if I had what's the probability of B given A, it's going to be the probability of B and A, which is the same as A and B, but this time it's given, it's out of the probability of getting A. All right. Can I just do up here, we worked out the probability by the number. In this case, we had, let's do it here. We did the number of P and C divided by the number. We could have done it from probabilities. So we could have said, what's the probability of getting, what are we doing? Pizza and coffee. It's 6 out of 25. Because there are 25 people that are in this class, divided by what's the probability of someone liking coffee is 16 out of 25. So whether you use the probabilities or the numbers, it's the same, because 6 over 25 divided by 16 over 25, if you know your fractions, you know you can cancel the 25s, and you're left with 6 divided by the 16. All right? So working from the number or from the probabilities. What about the probability of someone liking coffee given that they don't like pizzas? So that means we want to find the overlap. So write out the formula every time. The overlap of coffee and not pizza divided by the probability of not liking pizza. All right, so let's go back to our Venn diagram. Where's our overlap of coffee and not pizza? So people who like coffee but they don't like pizza are going to be this section here. So I'm just going to go 10, we'll just go with the number of people, divided by how many people don't like pizza? 10, there's all these 10, plus 1 makes 11. So there's a probability of 10 out of 11 that someone likes coffee, but they don't like pizza. All right. In this example here, that's just running through that proof of the formula that A given B, what's the chance of liking A, but we're looking only at B. So you don't consider all of that. Always start with what you're given. So start with given B, that part. So just look at your circle for B. What's the chance they like A? Here's the part of A. They're the ones that are in A that are in B. So B divided by B plus C, and that's just that calculation we did earlier where B over the whole probability, the whole number of people, divided by B plus C over the whole lot. This formula here is basically the rearrangement of the initial formula we were looking at. So the probability of A given B equals the probability of A and B divided by the probability of B. That's the one. So whatever is here is on the denominator. So basically, to get this formula, they've just multiplied this to the other side. They've multiplied both sides by the probability of B to get that relationship. So it's just rearranging, it's nothing new. All right, so the probability of A given B times probability of B equals A and B. Let's look at this example. We've got a class of 40 students, 32 like bananas, 22 like pineapples, 2 dislike both fruits. They dislike both, so it means we've got 2 people out here, a student's randomly selected. So if we've got 2 people out here, we need to work out, is there an overlap? So if there's 2 people out here, then the probability of, or the number, sorry, so the number of people that are in A or B needs to equal 40 minus 2, which equals 38. But we've already got 34 plus 22, so 34 plus 22 equals 56. So what overlap have we got? So therefore the number of in A and B must be 56 minus 38. All right, so you can see how we work these out. 56 minus 38, what have we got? Gives us 18. So if we know we've got 18 in here, fill in your Venn diagram. So that's 18. We've got 34 liking bananas, so we've got 16 in here, and 4 that like pineapple only. Okay, so have a go with these ones. Pause the video and then have a look at people that like both fruits, likes at least one fruit, likes bananas given, there's that given, that he or she likes pineapple, dislikes pineapple given that he or she likes bananas. So pause the video and have a look at that. Right, I've just put the answers in there. Have a check on those. If you're not sure, then we'll talk about that in class. This one here, the top shelf, I want to run through this example briefly, but I want to talk about it more in class. So we can just make a start here. Top shelf of the cupboard contains 3 cans of pumpkin soup and 2 cans of chicken soup. The bottom shelf contains that story. Lucas is twice as likely to take a can from the top shelf as he is from the bottom shelf. Suppose Lucas takes 1 can of soup without looking at the label, determine the probability. So the question is, are we in a Venn diagram or a tree? So ask that every time so we can work out which way to tackle it. Because we've got 2 things happening, then it lends itself more to a tree, and because they're mutually exclusive, again it lends itself to a tree. So you can't take it from both shelves, you're taking from one shelf or the other, and the can's either going to be a pumpkin or a chicken soup. It can't be a mixture. So because they're mutually exclusive events, then we can look at the tree. So mutually exclusive. So have a go at drawing that tree up and have a go at answering these. And then I want to add one more question that we can look at in class. So if we look at what was the probability of choosing someone that selected a can of chicken given that it was from the bottom shelf. So that's an extra question we want to look at. So have a go at setting that up ready for class, and this one as well. Number 4 we'll do together in class with looking at these ones again with conditional probability. So thanks for listening and looking forward to seeing you in lesson.